Hey, what's up guys? Welcome to my stream. Tonight I'm going to be working on trying to figure out why the font doesn't render properly in the emulator. So let's take a look at where we're at. So let's say if we just disable the trace. So see here we've got this sort of good looking introduction to the Vectrex when it loads. This should say Vectrex here, and then after that this should say like Mindstorm, and clearly it's not saying that, so something's up there. I actually took a screenshot of what it's supposed to look like to kind of help me debug it. So if we take a look, my Vectrex stuff, images. So this is what we're supposed to see. So you can see how the way Vectrex is written here. And in fact, I was reading in the documentation for this function, and it says that there's like 1, 2, 3, 4, 5, 6, 7. So you can see there's kind of like, it's made up of seven lines that are being drawn. So let's take a look at that. If we restart this, let's try and see if we can take a look at what this looks like. Continue. So if we pause there, it's kind of hard to see, but basically, I wonder if I use the magnifying tool. I'm going to try and use this magnifying tool in Windows, see if we can take a look. Make this bigger. Yeah, we clearly have way more than just 7 lines. But what's interesting is you can kind of see, anyway, you sort of can see it's in there, but it's a big mess. So what I'm gonna do to debug this is we're gonna take a look. I have a few ideas. Like one of my ideas is maybe to write a program and have the program just use the text function and just write one letter on screen. So that's one thing we could do. But before I even get into that, let me bring up the BIOS listing. And here, it's called print string D. Yeah. So I believe the function that's being called is one of these print strings. Oh, here it is, print string. So this is actually the function that's getting called to write Vectrex, for example. And I started looking at this function and started documenting it, trying to understand how it works. Actually, the comments in here were incorrect, which was super confusing. Where in places where it was saying, where now you see disable ramp, it was, the comments actually said enable ramp, so I changed them. And vice versa, where it said disable ramp, for example here, it actually should have said enable ramp. And that's kind of important because that explains when the beam starts moving and when it stops moving. What makes printing characters challenging is the fact that it's not using the timer. So basically there's the timer 1, which is typically used for drawing, is not used at all for text. So from the way I see it, this code is relying on the fact that it will turn on and off the beam and use the shift register to store the pattern. So let me just read here what it says. This is the routine which does the actual printing of a string. The U register points to the start of the string, while C82A contains the height of the character cell, so this is like the desired height, and C82B contains the width of the character cell, so this is the desired width, from what I understand. Now, the string is terminated with a 0x80. The string is displayed by drawing 7 horizontal rows of dots. The first row is drawn for each character. Then the second. The character generation table is located at, and it shows this here, only characters 0x20 to 06f, uppercase, so ostensibly that's A to Z, are defined. The lowercase characters A to O produce special icons. Now, if we focus on this 7 horizontal rows of dots and what it's really saying there, and we come back to this picture, is what it's saying is that, let's say the string is Vectrex, that it gets in, and the U register will point to the very first V, let's say, of the character in memory, will point to the V of the string Vectrex, and which is terminated by 0x80. So it's not null terminated, but it's 0x80 terminated in memory. And what it does is it says, okay, this algorithm says I'm going to write Vectrex by writing, let's say, this bit here, this little bit of the V, and this little bit of the V. Then it'll write this bit of the E, then it'll write this bit of the C, then it'll write this bit of the T, R, E, X, X. And then I believe what it does is it swings back, drops down, and then once again, then writes the next row. Now, furthermore, it talks about this character generation table. The character generation table, what it contains is, for each character, it contains a bit mask, or a bit map, really, of how the character should be drawn, right? So it'll have, like, I think it's 8 by 8. And for example, you can imagine for the V here, it'll have, let's say, 1, 1, then maybe 1, 1, 1, 0, 0, 0, and then 1, 1 or something, or maybe like, anyway, 3 1s, 2 0s, or 2 1, 3 0s. Actually, it probably looks like, yeah, 2 1s, 3 0s, followed by 2 1s, you know? So like something like 1 1 0 0 0 1 1. That's 7. I mean, I don't know if it's 7 or if it's 8, because V actually looks narrower than E, so I'm gonna guess it's something like this, and then maybe followed by a 0, right? And then it'll be like 1 1 0 0 0 again, 1 1 0. Looks like the third one, similar, and then after that it'll be like, you know, 0 0 0, maybe 1 1, or maybe a 1 there. I'm just, you know, shots in the dark here, right? Like something like this. Just gonna like pretend it's something like this. And that's 7, you know. So let's say that's how V would be written, and that's what would be in the character generation table. Actually, I think we can go see the char gen table. FD94 plus 20. So here it is, char table. Unfortunately, it's not super readable. We'd have to like take 1, 2, 3, 4, 5, 6, 7, 8. So you see each character here. Let's say this is A, right? So if we were to convert this into bits, maybe just for fun, we'll try and do that just for one of these. So like hex, that's 20. So if I could like copy the binary. So that's that. Then this is followed by 50-50. Okay, sorry, so that was 0020. It doesn't want to show it to me that way. Yeah. Okay, let's just keep going here. So 50-50. Then 20C8. Yeah, I'm starting to see the A already. 20C8, then it's 2010. We're gonna line these up afterwards. 1040. Then it'll be zeros, and then it'll be 8. I think what, okay, yeah, it's because I need to chop it off at it's basically 8 bits per row, so that's why it's not looking quite right here. 8 bytes, sorry. 2, 3, 4, 5, 6, 7, 8. I guess this has a 0 at the end. This would be something like this. Am I doing this right? Okay, you know what? Let's try this again. So first row was zeros, so it doesn't really matter. Next one was 20. Why doesn't it do that properly? It's just weird how it starts like that. Then it goes 50 and 50. Okay, there we go. Now we're starting to see it. See, that's like the top of the A, then 1, 1, 1, 1 here. Then we have 20, which is the same as here. Hey, Alvaro. 20 and then 10. How you doing, man? Then it's 10 again. It's surprising how this looks. Unless I misunderstand. Followed by 40. And then a bunch of zeros and then 8. So how's it going on my side? It's going alright. I'm trying to understand this character table here and how it represents characters. for the Vectrex. From what I understand, this is supposed to be kind of like a bitmap, and that because what happens is these values are fed in directly to they're fed in directly to the via the shift register. Five, 10, 15, 20, 25, 30. I'm not quite sure I understand how this works. So basically I was looking at the code for how how strings are printed to understand Does it say minus 20 though? Why does it say that? Minus 20. Hit the chart table, minus hex 20. And then here it says it's at F9D4 plus 20. Okay, that's F9D4. And what we'll do, let's run to here and see what my debugger says. We'll break there. So apparently it's loading F9D4.
I'ma get medieval on your ass.
That's strange, right? That it would actually load this address, which corresponds to some code. But then it does an offset from X with the value that's in A here. But A just points to, contains 1. Or am I right? Maybe not. No, here, okay. Oh, there we go. A. Oh, okay. I see. It's going to use the ASCII value of the character it wants to print as an offset. That's why it goes minus 20. Okay, this is a mistake. This should say minus 20. F9D4. Where's it getting F9D4? Oh yes, okay. Okay, yeah, I see what they mean. This is correct. So basically, chart table minus 20 hex is F9D4, and what they're saying is that from there plus 20 hex, you'll find the beginning of the actual chart table, which is correct, and that they do this because, let's say you want to write the letter A. So ASCII A. So A would be at 41 hex offset. 20 would be space. Only characters 0x20 to 0x6f are defined. Okay, yeah, up to O. So I guess they support all of these symbols, and they support space. Yeah, I guess that's what it means. So in that case, if that's true, then when we go, it's not the letter A that I was supposed to be mapping out. Okay, so I'm thinking space is zeros. I'm thinking how many bytes are they using per... It's like the first printable characters start at 20. Yeah, exactly. Well, yeah, exactly, right? So 20 is basically space. And then after, so I mean, if we consider this 0, 0, maybe that's what represents space, you know? So that would just be only 8 bits though, which seems like not enough, unless it's something like, you know, maybe it's like that, but that's not enough to represent characters, you know? If each one of these represented a bit. So that's what I don't understand. And if it was 0, 0, 20, 20, then it would be something like that, and then 20 in hex is 0, 0, 1, 0, followed by 4 zeros. So, you know, that doesn't look like a space. That's what I'm just trying to understand, like, are each one of these a character? Like, how does it work, you know? I guess I can look at the code and try to figure that out. Let's see here. This code, though, is not super easy to understand. That's why I put a bunch of comments in here. I think what it is that it is supposed to be... Oh, you know what it can be? Let me go look at that table again. Okay, I think what it is that space is split up. These are like the first byte is the first part of space, and then here's the next part, and then perhaps that's the next part, and that's the next part, and that's the next part, you know? I don't know how many parts there are, but you can see they're always starting with 0, so that there's a safe bet there. It's 1, 2, 3, 4, 5, 6, 7. So perhaps 7 bytes are used for the bitmap. If that's true, then maybe here 20, 70, 70, 20, 0, 0, 20. Yeah, see that I can see that being like an exclamation mark, right? Because like it would be like, okay, 20 looks like this. 0010, 0000, let's say, and then 70. What does 70 look like? Like that. Then there's another 70 over here. Then there's another 20, so like this. Whoops. Yeah, this is starting to look right. And then it's zeros. And then another set of zeros. And then another 20, which would be like this. Now that looks like an exclamation mark. And that makes more sense too because of the way the code was written for printing characters, is that it actually uses, you know, this first section to write the top row of the character, and then it jumps to here to write the next row of the character, right? So that makes a lot more sense. So that means that all the printable characters are right in here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Yeah. So I guess that makes sense, right? So are there, how many characters would there be, they said, in the code here? (20 to 6F). (79). Oh my god, says Alvaro. What? It's kind of freaking me out that on my dashboard I don't see the video preview working, but I assume you can see me, right? I always have problems with the Twitch dashboard. Come on. Oh, okay, it's working now. So I don't know, Alvaro, if you wrote something. I just saw OMG and then that's it. So yeah, so I think that's how it works. So that makes some sense. Like, I guess if we wanted to figure out where the letter A is, you know, we have to like go all the way to the 8th entry, which would be what, 66 minus 32, so 34. And I said that this was 2, 3, 4, 5, 6, 7, 8, 16, 32, so 33, 34, maybe this one here. F0, 8, 8. Let's see if that's true. So F0, 88 again. 0, 88, 88, F0. Oh, that looks promising. Yeah, so 88, 88, F0, then A0. Oh no, this is like the letter R, isn't it? I think I was off there. Anyway, let's just finish letter R. 0 and then 88. Which I already had. So yeah, there you can see that basically that would be the letter R. Okay, so yeah, you see me? So yeah, so there you go. Like basically it's stored that way. It's each one of these sections represents one of the printable letters, the characters that we can print. Each one of these. Oh, that's why I was counting it wrong. Okay, yeah, sorry, I was supposed to say this is like 16, 32. So A would actually be probably here, because it's each one of these represents two letters, right? So it says 8, that means it would be 16 letters, 32 letters, and I was looking for the 34th, I believe, so it would be here. So it should be 20, followed by 88. No, sorry, 20, followed by 50, followed by 88. That should give us the letter A. 20, followed by 50. 50, then followed by 88. That's starting to look like an A. 20, 50, 88, 88 again. F8. Then 88 and 88. Yeah, that makes sense. And there we have letter A. Now, what the print character thing does is it uses this table and it says, okay, let's print the first, for all the letters of our string, we're going to print the first row of each one. And it actually uses this here and puts that right into the shift register, and it enables ramp, so the beam starts moving in X direction at whatever like input speed, and the speed basically determines like the size, so that the so-called width is what's used as the value to feed into the X integrator for the via. So that's like how fast the beam is going to move from left to right. And then they put this value, let's say they'll store this into the shift register, and so the beam should go ahead and go like write nothing, write one, like write a part of a line, and then write nothing, you know? And then it'll move to the next character, and then it'll write the top row of that next character. And when it's finished writing the whole string, let's say Vectrex, then it'll say now we're gonna go and do the next row. So it'll move the beam back, go down, and then say now we jump, we offset ourselves in the table. You know, so our pointer will start here, then our pointer will be here, and then it'll draw the next row with the same idea, putting those into the shift register. So that's what it's supposed to be doing. So like in here, we can see that so here's it's gonna disable the ramp, so disable the drawing, and it's going to start setting up. It wants to set up the beam. So you can see here, it's gonna say enable mux, and this will clear the XY offset register, since port A is 0. Then after that, it does some stuff here, disables the mux, disable the ramp, set mux to channel 0, and then enable the mux to write a value into Y, which is to clear Y, because they want no offset and no Y, because they're not going to be moving the beam in Y, they're going to be only moving it in X. Then then apparently there's a delay. Again, the ramp is still disabled, so it's not moving yet. Disable the mux, so that the next value that's written should write to X. This is where it gets a text width, right? And then it'll send it to port A, which will set X to the value of this text width. And really that is the speed that it needs to move in X, as I was saying before. Then point to start of text string. So this here means into U we want to load, let's say vecstring pointer here will actually point to Vectrex, the string Vectrex followed by 0x80. And then here it's going to say enable ramp, disable mux. Enable ramp means now start moving the beam, right? So it's going to start drawing the very, top of all the letters of Vectrex, right? And then it'll branch into here, and here's this loop here, right? And it's very interesting. So it jumps here, and then it says, by the time we get here, and that's what's really interesting about this, is that it's all about like the number of cycles that have elapsed. It's really crazy, but it's like it knows that by the time it gets here, it'll run this instruction. This will take some cycles. The branch will take some cycles. This will take some cycles. What it does here, it says move U to point to the next character. So let's say Vectrex, it'll point to E now. Okay, the letter E. And then it'll say branch if plus to here. So this basically will stop branching once we hit 0x80. But while we're still within our string, it'll come up here. It'll load into A the value of A comma X. Yeah, and A was set to 1. Trying to understand what that is about. X basically points to the string, no, to the chargen bitmap. And A contains the character, the ASCII value of the character. So here it's saying I need to now store into A the actual address of the top row, let's say in this case, of the first letter. So let's say it'll put the address of the top row of the letter V. Then it takes that byte that's there. So if we come back here, let's say we were actually going to print A, it's going to take this byte here and put that into the shift register. This is really important. It writes to the shift register here. And again, the shift register is used, so when the beam is moving, the value in the shift register is used to know, does it write or not. If it's 0, it's basically blanks, so the beam shuts off, and when it's 1, the beam turns on and writes. Okay? I'm pretty sure that my problem with writing has to do with the shift register, because that's really what drives what's written on the screen. And my feeling is that probably there are points where I'm writing because the shift register contains values in it, and I'm probably not clearing the shift register correctly. And I don't know what clears it. There's a set shift register mode up here, which makes me wonder, does setting the mode also clear it? I don't know. That's a possibility. It's very possible, actually. Although, I don't know. It doesn't get cleared again. So, anyway, keeping that in mind, it stores that value there. And all this time now, like, the beam has been moving, right? Because ramp was enabled here. So in the time from when it was enabled, we branched to there, we loaded, we branched again, we loaded again, we stored into the shift register. and now the beam has been moving, and now the beam starts to write. Okay? And it'll start writing, and then we'll get the next character, and again we'll branch to here, get its thing. So see, it assumes that by the time it's executed this, and this, and is about to store the next one, it has already, the beam has had enough time to write the top row. And I guess that makes sense, because at its maximum speed, it can write 1 pixel per cycle, right? And so it would only need like 7 cycles to write 1 row, but we're definitely not moving at maximum speed here. We're moving at some slower speed, so it'll write less, it'll need more cycles to write those pixels, but you know, I don't know, I don't remember how many cycles these take, but surely enough that by the time we get here, we can write the next character. So like, it will have had enough time to have written out this, and then the beam would be here when it's time to, you know, maybe the beam is over there in the middle of the V and the E when we write out the, let's say the top row of E into the shift register, and then the beam will say, oh, okay, now let's turn on and write those, and then turn off, you know, and then here we will have written for the top row of C into the shift register, at which point it writes that. Now there's so many things here that can go wrong. Like, from the way I understood the shift register is it's always shifting back in, right? So like, if the beam had enough time, it would start to write the beginning of V again, right? So let's say start to write V, wrote V, and then we, you know, the beam is drawing. We need to write into the shift register before it would start redrawing V again. And that may be where part of my problem is too. Like, the timing where with, you know, the cycle timing of writing to the shift register and when the beam actually starts using it. There may be like a delay there that I'm not emulating. So there's a possibility that that's part of it. These are just ideas. I'm thinking of different things that could go wrong, knowing the implementation I have. Now, eventually, we'll hit the terminator, right? We'll hit the 0x80, so then we'll go down here. And then here it says, we load X register. I wrote this comment here. We're going to load the X register with the negative width, ostensibly to move the beam back to the left. And I wrote here, but it seems the shift register wasn't cleared, which means it will draw the last pattern on its way back. That can't be right. So that was my thinking when I wrote this. I was reading this code yesterday. So if we look here, it disables the ramp, so it stops the drawing, or stops the moving of the beam. And it writes, see, negate the text within the DA. So this is basically, once you do this, this will write the negative X value, like it'll write this value negated into the X register for the VIA. So that means now the beam wants to move leftwards when it enabled ramp. So we load A with 1, and then here we actually enable ramp with that. So now the beam will start moving to the left, right? Here we're checking to see if we're at the last row of the charge end table, because it needs to do all like 7 rows. So in our case, as we just started, it will have only done the first row, so this is not done yet, so we won't jump down. Point to the next charge end row. So here it'll say load X with an offset of 50 in hex. So that basically should point us to the next one. So it's 50 again. So that's 80. So it'll like move 80 bytes forward. So I'm guessing from here to here it's 80. Let's see. FA43. Minus F9, F3. Yeah. So that moves us to the next one. Here we get the string length. Transfer D, transfer U into D. Why does it get the string length? See, this all this code here, I'm trying to understand it. Like there's like a lot of delays. There's like a subtract by 2. U actually is supposed to contain the beginning, the current character in the string. So at this point, U should be 0x80. So I don't quite understand what this is about. Transfer U to D. Then subtract D, vex string pointer. Then subtract B, O2. Then shift left key. -2 multiplied by 2. Delay a moment. Load A81 not. Decrement B. Branch if not equal to this. So this is like a delay some more in a loop. So it's like as if they did some computation here based on the length of the string that is like how many cycles we need to loop to give enough time for our beam to move back to the beginning of where the string, back to the left edge of the string for the next row. That's what I'm getting here. And then after that, it disables the ramp, so stops the beams moving. So the beam now, let's say, would be back at the beginning of where it had drawn the first row. And then here you see it gets the text height. So now we want to move the beam down, right? Get the text height. And now we want to store that into Y. So to do that, we need to write it into port A, enable the mux so that Y gets the value. Then we disable the ramp, disable the mux. Okay, so sorry, we enable the mux to write Y. Now we disable the mux and clear DA to write to X. So basically this is clear X reg. And this here is enable mux write Y reg. Okay, then we enable ramp. So this here, it's interesting. You see, it does this and then this. This is to move the beam down. And you can see, like, it doesn't give it much time, right? It just wants to move the beam down just a little bit, like enough that the time of enable disable should just get us down to the next row, it would seem, given the speed we stored in Y. This is where you really see like the kind of finicky code you have to write in order to control this analog beam, you know? I mean, this code was written for developers in the BIOS, but from what I've read, a lot of developers, in order to really get the most out of their machine, would often end up writing their own version of these functions. Like this print string function, you wouldn't want to use this in gameplay because it's extremely slow and wastes a lot of cycles. You know, so if you wanted to have some text in your game, you'd probably end up writing your own, much more optimal print string routine to show scores and stuff. And then you'd have to deal with finicky code like this, you know. And I don't know if they had the source code to the BIOS, so they'd have to like kind of just, you know, do the same thing that this person did, was, you know, disassemble and comment it and understand it themselves. So that sounds like it must not have been that fun. Then here, this is kind of surprising because here they load into B the value 03. And as the comment wrote here, I added this like arrow, but it said here 0x what enable ramp with a question mark. And this is kind of surprising because then it jumps back all the way up here for the next scan line, right? And see here, it stores that B value into via port B, which initially said disable the ramp here, right? But in this case, whatever the B value has would enable the ramp, which is extremely strange. So like this comment would be untrue on for the next row, but that makes little sense. So I'm not quite sure what that's about. Because see, like here storing B, the B value that gets stored here comes from over there, where the top, if you see 8 here, that means bit 7 is set. And if bit 7 is set, ramp will be disabled. But if bit 7 is not set, then ramp is enabled. And that is indeed the case here where we load 0, 3. That 0 means that the ramp would be enabled if this got stored into there, which it is. So that's just funky. And you know, maybe that's part of the problem. I mean, obviously there's no bug in the BIOS, right? So maybe there's something we don't understand. Me and the person who disassembled this code. Like, how can this be, you know? And maybe what's happening is we are enabling ramp and it just starts moving and drawing a bunch of crap. Like see over here when we say enable ramp, we're storing the value of A, and the value of A is 01. That O here is what causes the ramp to be enabled. But here, every time we write B, it's because we're assuming B has a value like this, where 83, where the 7th bit is enabled, which means that ramp would be disabled when we write that value to port B. So I just don't understand this part here. Yeah, I don't get it. I don't know why the person who disassembled this wrote enable ramp here. Maybe they just misunderstood, because like I said, everything was inverted. But basically, you know, everything we've read says it, that like ramp is enabled when it's pulled low, and bit 7 is directly connected to the ramp line. You can see it even in my code here. Port B. See, like ramp disabled is bit 7, and see when it's set, it's disabled. That's why I wrote it this way. And when we want to check if we need to draw, if integrators are enabled, meaning that the beam is going to move, we check that port B's ramp disabled isn't set, meaning that it's 0. So I think the person who was disassembling this wasn't sure, hence the question marks. So many things can go wrong, and I'm not sure what the problem is. But one thing that I did think about trying is like one thing we can do is, let's say I put here a static bool enable clearing, and I'll set it to false. Okay, let's say enable clear, and I'll say like if enable clear and this. Now I set it to false so that we don't do any clearing, and the reason why I want to do this is if I launch my debugger, I think what we can actually see is each bit of the font rendering, one bit at a time, as long as we don't clear. Because the thing is, we're always clearing right now at 50 Hertz artificially to just kind of simulate a little bit what it's supposed to be like, and then that gets in the way when I'm debugging, because when we debug, we basically max out our time for each delta time right away, and so we clear on every single step, which sucks. So if I just don't clear anything, and what I do is I run up until, look here, we want to go in all the way until, let's see, yeah. So like this is the loop that basically draws the little bits of each character, right? So let's say we go to F4 C5. So we add a breakpoint there, and then we're gonna step, and just by stepping from there, we should see something interesting on the output. So let's go there. And let's step. Step load A. Ah, look at that. There's a little line that just appeared here. I don't know if that's probably not super visible unless you have like a really large screen. Can I stop that magnifier? There. See this little line here? So if we look back at the code here, you know, one thing that would help is to get symbols in there. And let's do like the next bit, and then I'll show, because basically we wrote the pattern. So there, more lines just got drawn. And see here, we did store 0A into the shift register, right? I mean, it's the same thing we did up here, just I didn't have the symbol, like the symbols to show that this is the shift register, but it is indeed the shift register. So here we had stored a value into the shift register for the very first character for V, and now we've just stored the next one. So if we keep stepping, so I think we're supposedly done writing our very first row. So let's take a look at this again with the magnifier. See what this looks like. Actually, not the magnifier. Forget that. Let's take a screenshot of the first row. Okay. Interesting. If we take that other image we have. Very interesting. So this looks like this would be V, E, C, T. We're missing something. But I'm pretty sure now we actually got to the point where we're done. I guess I can count this. 1, 2, 3, 4, 5, 6, 7. So we did do 7. Let me just step a little bit further because maybe it needs to do a couple more updates to draw the last bit of line. So now we're doing the negating in there to go backwards. But yeah, it doesn't look like we're... Oh! It did draw something. But see, that might be... Yeah, that might be where we start overwrite. Yeah, this is where we start messing things up. And you see the beam is moving back and it's drawing what was the last thing written in the shift register. So this comes back to my question about, like, how does it actually work with the shift register? Since it never clears it. Unless I misunderstand how the shift register really works. So if we look here. Because, you know, what we do with the shift register, if you look in the code. Okay, so this is shift, right? Now when we write into the shift register, we put the value in there, which is some kind of bit pattern, as we saw. And then I have this little hacky thing, but I have this update shift. This is a function that's going to get called it's going to be called every cycle. And what we do in there is we every 2 cycles we have here, we read bit 7, so the top bit we store it here. Then what I do is I basically roll it, right? So I take the shift and I shift left 1 and I take bit 7 and I put it into the 0th bit position, which is what this is about. I want to make sure that I wrote the code correctly. Yeah. And then we set blank to the value of in bit 7. So basically, if bit 7 is 0, we want the blank. If bit 7 is 1, we don't want the blank. So the way that works is that blanking determines... Oh, so that must be the trick. Oh, sorry, I'm thinking. Basically, we... So if you think about like the bit pattern here, 0 means we want blank to be set. So like we wrote this into the shift register and it'll shift out the top bit here. And that bit 7 will then say, okay, for this guys, we're blank, which means don't draw. Turn off the beam. Turn off the beam for the next one. Turn on the beam. Turn off, turn off, turn off, turn off, turn off, you know? So that's actually what it's supposed to do. The thing is, it also rolls it back into the bottom, right, of the shift register. which means that if you don't do anything and the beam keeps drawing, it will eventually repeat the pattern, which is the whole point, is that it allows you to make a pattern and then just have the beam move and it'll draw that pattern. So like I said, the code has to be, you know, the drawing of the characters have to be fast enough so that it doesn't get a chance to draw the pattern again. But then, like I said, when it's done drawing, let's say the first row, it's gonna have whatever pattern in the shift register was there for the last character, right? And then it's gonna move the beam left. And I mean, I don't see blank get set explicitly, or shifting being disabled or something. Six, seven. Yeah. And you see, then we keep looking here. What disables shifting and what disables blanking? Let me go see here. Blank. Oh no, it won't be in here. Blank. Okay, because blanking can also be set through this register here, which is the peripheral control register. Right, but I don't see any writing to the peripheral control register. 0xb here. Is it B? No, C. This guy, what's called via control here. In fact, it's like very rarely written to this via control. So it doesn't seem to be what would work here. I see like clearing of the shift register in a few places. Clear shift register, blank output for drawing lines. Drawing patterns, here's a clear. And here we are, save and shift. This is the code we're looking at, print string. But then there's nothing that clears it. Alright, one thing we can do to debug this is let's look at the actual patterns that get written into the via shift register and see if it looks like the tops of what Vectrex would look like. That's a good idea. So start again. Let's put our breakpoint again to... Where had we stopped before? Here. Let's go to F4C7. Break there. I have my keyboard. Okay. Break it. F4C7. Oh, and let's also last time. Let's load our symbols. And now we're going to put a breakpoint into the writing of the shift register. Here. So let's step. There, we just got a write into the shift register. So let's take a look at what that looks like. And it got 0. Or, I don't know if, no, I don't think I can trust this because, okay, there it is. So here you go, we can see that value B has this pattern here, which does look a lot like the beginning of a V actually. So let's actually track this. So that was the first one. So you can see like 1, 0, 0, 0, 1. That would look like the top bits of a V, right? The next one should be like a pretty solid line of 1s, maybe with a couple zeros for the beginning of E. So now we'll step again. Yeah, there you go. That looks like the beginning of E. So that's the top row of the E. Then should be the top row of C, so probably just a few less 1s. Yeah. See, that would be C, the top row of C. After that is T, so T should also be so a few more 1s, yeah. So in fact, E and T have the same number, like the same length at the top, which I guess corresponds here. E and then T, yeah. R will be slightly shorter. So this is for R. You can see it's shorter by 1 bit. Then we should have E again, which looks like this. Sure enough, same thing. Then it's X. So X should be a bit more interesting. Yeah, so X looks like that, which actually looks a lot like V. In fact, it's the same as V, at the very top row anyway. And then we should get nothing written anymore. So the last bit pattern is that one of X, right? See? Now we're going to start moving left with that last bit pattern written in there. And like nothing that I can see, unless like writing to port B would do something, but I don't think so. I'm just wondering, like, what if I don't let the bits cycle? So like, basically we only write the pattern once. What would that look like to us? So basically don't do this. Don't OR in bit 7 in the bottom. But use it to set the blank. So basically we're just purely shifting and dropping the top bit. It'd be interesting to see what that looks like. Break there. Wow, totally does not do the same thing at all. That's very telling. Now I'm starting to suspect that maybe this code for updating the shift and then actually using it to draw isn't doing what I think. Oh, you know what it could be? Of course. It totally makes sense. The problem with what I'm doing here is, like, the number of cycles here can be quite large, right? And what I'm doing is, when I do update shift, is I'm just shifting out the bits and then I'm doing drawing. So, like, it's like I don't have enough granularity here, you know? I don't draw. Basically, what I mean is I'm probably skipping bits in the shift register because my number of cycles is too large. Like, if cycles were 10 and basically we shift after every 2 cycles, you know, right? I would end up shifting out 5 bits and then I draw based on whatever the last value of blank was set based on the last bit I shifted out. This is total garbage. Yeah, this totally will not work. If I put a breakpoint here, okay, let's put a breakpoint here and I'll show you what I mean. Okay, let's do the next row. So here, whoops, here we end up writing to the shift, the first one for, like, the next row for V, which actually looks a lot like the first row, which makes sense. Yeah. And if I put a breakpoint now in here, show me the number of cycles. See, cycles is 4, right? So that right there is too many. The last instruction we executed was 4 cycles long, and so we're gonna end up doing like 2 shifts in here. So we like lose bits. So clearly I'm not doing this right. I need to, in fact, what I need to be doing is I need to be looping per cycle and, or maybe per pair of cycles there, but basically per cycle, and drawing in relation to the shift. Not updating shift separately and then drawing. I need to kind of you know, shift, draw, shift, or shift, not draw, shift, then draw, shift, not draw, you know what I mean? And this way I basically capture the drawing per bit that's in the shift register correctly. So that part will explain why I'm not actually drawing out everything correctly going from left to right. It doesn't at all, though, explain why from right to left it doesn't work, unless I'm right and I'm not supposed to actually rotate the bit. But that seems wrong because everything I've read about the shift register is about drawing patterns. So unless there's a way to control the shift register that I don't know about, there is a section in here all about the shift register. there are all these different modes, but as far as I can see, there's only one mode that's ever used, which is this one here. Shift out under control of O2, which is the phase 2 clock. I had a... Yeah, this here. This person who had written about emulation deficiencies. Shift out under O2. I should say 2 cycles, not 8. So it's 1 cycle, 2 cycles, 1 cycle, 2 cycles. This basically means shifting a value starts 2 cycles after via shift register was accessed, not immediately. So that's something I'm not quite doing. There's a delay of 2 cycles, technically. Remember, drawing usually uses the shift register. The value shifted results in the blank signal. But it doesn't talk about the rotating of the bits. This one might, though. Okay, this is interesting. In addition to a solid line, there is a sufficiently curved possibility to draw a dotted line. For this purpose, a shift register is used. We enter the necessary pattern there. For example, A, which is 0, 1, 0, 1, 0, 1, and say 6522, that the shift must occur automatically. Once shifted, each bit crawls onto the blank line, and thus the beam itself turns on in units and turns off at zeros. So it turns on at ones and off at zeros. The problem is that after 8 shifts, 1 zeros remain in the register, and all our remarkable dotted line breaks off. Aha! So here he's talking about how it's a problem, the fact that you have to reload the shift register. But this actually confirms what I was just now suspecting, is that we don't rotate. We really just shift. So it's not like a roll. So like what I'm doing here is correct. We don't want to put it back into the low bit. So that would explain a lot in terms of how the characters work. By the time it's finished drawing the last one, it can move the beam left because there's zeros left in the shift register, which he says here is a problem because he wants to be able to remake the pattern. And I think he goes on to say that the problem here is that even if you put in the same value again in the shift register, there's a delay that occurs so that you don't get a nice clean 0-1 pattern across, because by the time you write, there'll be a gap in between each one. So he says, under such conditions, it is very difficult to obtain exactly the dotted line that you want. Okay, so now I'm feeling more confident about removing this here. So we just literally just do shifts. That's it. So actually, we can since that's the case, we can simplify this code, right? We can say that just shift left by 1. And we just want to say, we don't have to do test bits, we can just say here, you can do a boolean, because this is a bool, right? So we just do test bits, because I have that for that. And we say, if it's not, so if it returns false, then we set blank. So that simplifies this code a little bit. I'm also still not even, I'm not even sure about the every 2 cycles part here. So that's another thing to check. But that's easier to check, like we'll see about that after. So if we continue here, take off my breakpoints. Interesting. The reason why it's not actually animating is because I would need to put back that change I made in here, enable clear. If we put this to true, if we allow clearing, just to see. There we go. So this actually looks better, believe it or not, than what we had before. But we can see the problem is what I was saying is we are not so could I like hack this quickly? Let me see. Having an idea here of like what if rather than do it this way, like let's just run all of this in a loop. While cycles minus minus is greater than 0, then instead of doing cycles here, we'll just do it like let's go like this. Cycles left is equal to cycles. Okay. And we'll just like do a quick hack like that. Super hacky there, but just so I don't have to change all my code here where I use cycles. We'll just do 1 cycle at a time in there. And then while cycles left minus minus is greater than 0. So let's see if this works. In fact, I should even do it for the timers. Because the timers also control the time at which the beam gets turned on and off, right? The ramp, timer 1 anyway, turns on and off the ramp. So this will actually give us this specific cycle when it turns on and off. So let's see. Holy shit. Look at that. Oh my goodness. Alvaro, are you there? Bedlam? Why does it say Bedlam? Do I have a... Hold on. I gotta see. Did I forget that I'm actually loading a cartridge? Oh my god. I'm actually loading a cartridge. All this time I thought I was not loading a cartridge and launching Mindstorm. Holy crap, this is so cool. Alvaro, man, did you see this? Mindstorm. It freaking works. Now I think it's gonna stay here because I don't punch any, I don't input anything. Oh, wow. This is amazing. It's so cool. Like I'm like super tempted to see like how I could kind of feed in just a button press just to see it actually go into Mindstorm and see the ship dropping everything. Let me see quickly if I can figure that out. Where would I have information about input? Look at the BIOS. Joystick. Init joystick enable flags. Vec joy mux 1. Let's see. Joystick 1 X enable mux flags. Okay, this is just memory. Joystick 1 Y enable mux flags. Joy analog, joy digital. These routines read the current position of the two joysticks. Alvaro, you saw? Here, let me show you again. I don't know, I guess you missed the big moment, right? I'll restart there. Check that out. Hey, ABDCW. Looks like you came right on time for this awesome moment of actually drawing properly. Okay, so let's see if we can just like fake button presses, because if we can, then we'll actually get inside the game, and that would be super cool. So the joystick enable flags C81F to C82, C822 must be initialized to one of the following values. Okay, so I assume the game will set this correctly. And the joystick values are returned in C81B, where the value returned corresponds to the mask set in there, and so on and so forth. Okay. So let's see what it does in the code. Set analog mode flag pointed to first pot. Read it if enabled. Enable mux and select pot. Okay, so it does this through port B. Output 00 to DA. Okay, so this is like basically going to use the mux. I remember that seeing something about disable mux, enable mux and select pot. Disable mux. So let me see here. So it must be one of these, because this has to do with sound. So it stores 1 into B. Enable mux and select pot. No, sorry, no. That's not at all what it's doing. It's storing in here. A has whatever value was loaded into it from X. And X has gotten the value from this Vec Joy Mux 1X. 8F. Enable. This really corresponds to what's known as the joystick enable flags. Joystick 1X enable flag. Enable joystick enable flag 0103. 01 and 03 looks like it corresponds to enabling joystick 1's X and Y. That's what this is about. So by default, joystick 1, X and Y are enabled. Sure. But this more joy analog, joy digital. Check analog flag, branch if analog. Enable mux test comparator. So it is really this comparator thing. And then output 40 to DA. And then test comparator. So really it looks like that comparator bit is what we want to set. So I wonder if I just set the comparator bit to 1, if that'll be enough. You know, bit 5 here? Like, what if it's always 1? Like, as though we were always pressing it or whatever. Let's see if that's enough. So when we write to B, port B, let's do set bits, port B, bits 5 to true. Hack, enable comparator bit, joystick on. I don't know, let's see. The fact that we're not moving from here makes me feel like this is not working. Okay, let me look a bit more. Because 40 is bit 5. Or is it? Bit 6. Oh no, sorry, this is writing with value into there, but it's checking bit A against port B. So here it reads port B. What's in A? 20. Yeah, so that's right. So 20 is indeed bit 5. So it loads into there and it's checking. So let's see. Then if it did test, if branch not equal to there, if it is equal though, it comes here, clear B. Store AD result. Okay, yeah. It's basically going to put the result into x minus 5. And it'll clear be in the case where the bit was not set. Branch if not equals. And what does B contain? Sort B into there. Load B 40. Let's see, it wants to write 40. The value 40 that it wrote out. So it's either going to write 40 or 0 at this offset here from x minus 5. Oh, that's interesting. Up here is another test for another comparator test for bit. Oh, so maybe I need to set both 40 and 20. But what's 20? Oh no, sorry, no, that is the one we're worried about. This is the test. Let me see, if I put a breakpoint here, F21B. Oh, well, that's interesting. We don't even make it there. That's kind of telling. F1, F5. Do we even make it to that function at all? Whoops. Where are we right now? F1A0. F1A0. So we're not far. We're here. Wait, recalibrate. Okay, no, that's just because we're waiting for that's totally normal. F1A2. Yeah, then from here, I want to see, like, it looks like we're not doing much per frame. So let's see what's happening in one frame. I mean, it looks like we're doing a lot of writing, printing of strings, which is not surprising. Dump this in here and see if we can find something interesting. Anything related to joysticks? Nope. Read button masks. Aha. That looks interesting. And then vec button state, vec button state, vec button 1-1. So this must be the code that's dealing with the input. So let's go take a look at that. F7 C9. Or not. Okay, no, because that must be... Oh no, it should be in here. F7 C8. Why does it say C9 here? F36A, F7C8, F7C9. F7C8 is read button masks. And before. Okay, both of these routines read the button states on the two joysticks and return their state in the following RAM locations. Okay, so what is this guy doing? Sound chip register E to port A. Sound BDIR on BC1 mux off. So it's talking to port B and A as expected. Doing some stuff, and then we do read buttons. So we have to read from port A. Okay, so it's not as simple as I thought. So basically you gotta set it up so that when you read from port A, you get the values of whatever joystick port you're listening, like you've configured it's to read from, I suppose. Check for transitions. COM A. It's COM again? Complement memory location. Oh. $1901. Store A. Store 19 into port B. So 19 means 0001. So sound BDIR would be enabled, sound BC1, and disabling of the mux. That is pretty much what it says here. Beater on, BC1 on, mux off. So I think I read something about how the joysticks are accessed through like the sound chip, or like they're connected, which is why we're seeing sound code here, like sound stuff in relation to reading joystick buttons. So maybe what I could do is in the reading of A, let me see here. Store A, point B, pause, store B to port B. Sound beater off, PC1 off, mux off. So you turn it on, turn it off. Clear DDRA to input. Clear. And 0901. So this is just PC1 on, mux off. Store A. There. So it's 09. And then we read buttons. So what I could do is I could say if B has like BC1 on, then return ones in A. Maybe that's converts to active high. What? This complementing of the results says convert to active high makes it seem that actually returning zeros would have returned ones. F1 D5. So here we are. So load A from the value in port A. So you see we didn't have zeros there. We have 0E. And the next thing is going to complement A, which if you look at our registers means that A will have F1, which is interesting. D5. Okay, so we're about to step on the reading of A. So what if I just force it now, A to have 0 in it? See if I had E. In fact, we were about to run, load A from there. Zero E. So what if it had 0 in it? So now we get 0 into A, and then we will complement it, which means that if we look at A, we should have FF. So I wonder if that's enough to make this move forward. Disable 1. Apparently not. Maybe it's looking for, you know, that you pressed and released or something like that. Okay, you know what? I'm gonna stop here. I'm gonna read more about input, and next stream we'll try to implement the input, and hopefully we'll actually see something here. This is really cool. I'm very happy with the progress. Let's just take a look at it again. It's super cool. Thanks, Alvaro. I really wasn't sure if I'd hit this tonight, you know, like I was really not sure. So let's check in. Let me commit my changes, and in this way next time I'll resume from where we are here. I'll say here for cycle accurate drawing, we update our timers and timers, shift register, and beam movement one cycle at a time. So that I won't check in. Oh yeah. But here's the main thing. So this did not work, so I'll just remove that hack. Yeah, and this I want, definitely. So, stage that. So I'll write here, fix font rendering. It's not just font rendering, of course. I'll just say fix rendering. And then here I'll say shift register no longer rolls bit 7 into 1 or into bit 0. It's only supposed to shift out the bits. Also made line drawing cycle accurate by updating timers, shift register, and beam movement on cycle at a time. And then while I'm at it, I will also check in this little change. I made a small change to my config, my configuration file, my options file tokenizer, so that I can use semicolons for commenting. So I'll say here option file now ignores lines that start with semicolon or commenting. That I will not check in, so let's push this. And yeah, I think I'm going to stop it here. So thanks for watching. Thanks Alvaro for hanging out. ABDCW. And if all goes well, we will resume next week on Monday. So thanks guys. Talk to you soon.